In more detailed look at superposition of waves, it's very important to distinguish between two types of wave velocity, namely the phase velocity of the wave and the group velocity of the wave. And we'll see how that arises here. For the sake of argument, let's look at two waves. I'm going to use the plane wave approximation, although similar kinds of results occur for spherical waves. But for us, I'm going to look at two waves simultaneously going through the same media. I've got them both going in the same direction. They could be going in opposite directions. But for the sake of simplicity, I want them to both be of the same amplitude and both going in the positive x direction. The only difference is they have slightly different wave numbers and angular frequencies. This one here has a little longer wavelength, so k is smaller, and this one here has a little shorter wavelength, so k prime is larger the way I've got it drawn, and it doesn't really matter if they're larger or smaller. We'll just assume that the relationship between k prime and k is this. K prime is equal to k plus delta k, and so that seems to indicate the larger wavelength up here gives a smaller k, and so and the shorter wavelength gives a larger k prime, and so there should be a additive difference here. Likewise with the frequency, I'll assume we know that the frequency and wavelength are related, and so they will have different frequencies as well, and I'll assume their frequencies are related by a similar fashion. And now then what I want to do is I want to look at the linear combination, the interference, if you will, between these two waves of same amplitude. I'm obviously using the complex representation of plane waves. It's a little easier in this. You don't have to do it, but you have to know some pretty gruesome trigonometric identities, and this way you don't have to remember as much. So one of the advantages of this complex form is it reduces your reliance on a bunch of obscure and arcane trig formulas between sines and cosines. But we'll look at the superposition of them, and so E1 and E2, and the combination is E. So we're superimposing two waves, and I'll go ahead and substitute in the k prime is equal to k plus delta k here. The first wave I leave the same. You can rewrite this one using the properties of exponents as kx minus omega t, and then an e to the I delta k times x minus delta omega t. So I'll factor out this piece from that exponential. And that's just so that I can take this outside the whole thing. In fact, I can take an a out, and I can take this exponential factor out, and I'm left with this. And then, as will become clear here in a second, what I'll do is I'm going to write this one as the product of these two, really this divided by 2 times another one divided by 2. And so I think if you look at these two and then use the properties of the exponents to combine these, they'll reduce to this one up here. And then what I'll do is I'll write 1 in the form of this number here times its inverse, which is just e to the minus of that. So clearly this times this is 1. And that allows me to factor out another factor, namely this common factor here. And when I factor that out, I'm left with e to the, well, I'm really left with e from this term. When I factor it out, I'm left with e to the minus I, so that's this term. And when I factor this out, I'm left with this one, so that's the first term. So I switched the order as well. And then that's sort of trying to multiply and divide by 2 so that I can recognize this one here as the cosine. So I've decomposed this into two forms, really into two pieces. And the way I look at it, this is sometimes called the modulation portion of the wave, and this one is the carrier portion. Uh, if if now you'd like to take the real part of this, because that's really what you do ultimately, uh, then if that's what you're doing, you'd get a cosine term of this. Or if you wanted to, like the convention where you wanted to use sines over here, you could get a cosine sine. So, and now then I can take a look at these, and if you look at the average value of k, uh, that's k prime plus delta k over 2, and this one is k plus delta k is k prime, so I get 2k, and so this k plus delta k over 2, that's this factor here, is just really the average value. Likewise, for the average frequency, if I take the average between omega prime and omega, the frequencies of the two respective waves, then again, using our definition that omega prime is just omega plus delta omega, you get this factor. You get a factor here that is like this term. So, I'm sorry, you get this term and this term are these two. Okay? And these just have the delta k's in them, so I leave those the same. So if you like, you can write this as k average here, and this one as omega average. Okay? I'll just leave it in this form though. It's pretty clear though that so long as delta omega and delta k are small departures from k, then this in general will be a large number, and if this is a smaller number in comparison to it, then these two can become negligible compared to this one. Okay? Likewise over here, if you can't do that in this case because I don't have anything, these are of comparable quantity. Okay? So as a result, I usually would lump all of this together. You see the maximum value is going to be twice the amplitude of one of the waves, and all of this with this cosine term is the modulation. So in a sense, it's like a varying time, a varying amplitude, and this other portion is the carrier portion, and it has effectively something that's really k average here, and omega average is like a fixed wavelength and frequency, or k and omega. Moreover, you can take it to look at some comparative things. The carrier wave. Let's look at omega maybe. Omega is large. Remember, delta omega is relatively small, and so the carrier frequency has a very high frequency component. And on the other hand, the modulation portion here, the delta k is small, and so the wavelength is large, right? And so the modulation is going to be this envelope really that sort of modulates the amplitude of it. In any event, you get two pieces, and depending on how you define the velocity of the wave, If you're looking at the envelope, which is one thing that the eye tends to do, is they fix on this maximum, you'll see that it moves with a fixed velocity. So the envelope, the modulation, moves with a different velocity than the carrier portion in general. In fact, they can even be going in opposite directions depending on relative values. Well, remember, for any wave, the wave velocity, these are both waves, so any wave velocity is just the part, the omega portion divided by the k portion. So for our cases, for the modulation, you'll see that the omega is delta omega over 2, and the k is delta k over 2, and I take the ratio of those, and they give me a velocity that's of the modulation. That's usually called the group velocity, v sub g. The 2's go out, and it's just delta omega over delta k. On the other hand, if I'm looking at the carrier portion, that's this piece here, then I do the same thing. Omega over k is going to be omega plus delta omega over k plus delta k. And it becomes simply this. And that's the phase velocity. What you really do now is you let delta k and delta omega get very small. So they tend to zero, they become infinitesimals. And the group velocity is then d omega dk. So I have to have a frequency that depends on wavelength for this to exist. And this one here is I let delta omega and delta k get small. Well, they're already small, so I can ignore those, and so it just becomes omega over k. And that's the phase velocity, or b sub p. So one can associate, depending on which one you're focused on, either the modulation, which moves with group velocity v sub g, or if you're looking at the carrier wave that's a part of it, then you're focused on the phase velocity and how fast it's moving, which is just omega over k. Well, if you remember, what we had been calling the wave velocity was omega over k, and so technically what we should, instead of calling it the wave velocity, we should have always been calling it the phase velocity. And but that's rarely done, especially in lower level courses, and even in upper level, it's assumed that you know which one you're talking about, and so and typically wave velocity, if they don't say anything else, is always going to be the phase velocity of the wave.